Hey there everyone, this is the Primetime Unit Test Review. I know everyone was expected to either do this in class or complete it at home, so if you would like to, get your unit test out or get the review out. We're going to go over the answers. Pause when you need to, replay anything that you found to be difficult, and we're going to get started. Up first, we have question number 1. It says, find the prime factorization of each number. Write the prime factorization using exponents and show your work. To find the prime factorization, we're going to use the factor tree method here. So for the number 40, I'm going to break this number apart. Remember, any factor pair works. I'm going to choose to use 4 and 10. And I'm going to use this because I know that 4 times 10 gives me 40. Here, I'm going to break 4 apart a little bit further. I'm going to go 2 and 2. Now remember, when we reach a prime number, we go ahead and circle it. If we see that the number is still composite, we break it apart more. 10 is composite, so I'm going to break this apart. A factor pair I'd like to use is 5 and 2 here. These are prime as well, so these are my prime numbers and the prime factorization for 40. Now to rewrite this, I'm going to write my numbers in order. 2 times 2 times 2 times 5. And we are going to write them using exponents because that is what the question said to do. So I'm going to go ahead and count how many 2's I have. I see I have 3 2's. So I'm going to write this expression as 2 cubed. The 3 came from the amount of 2's that I saw, times 5. And this is my final answer for the prime factorization of 40. Moving on to the prime factorization of 112, I'm going to break this apart. Knowing my divisibility rules, I see that this number ends in a 2, so I'm going to go ahead and try to divide this by 2. When I do this, I get 56 and 2 for the factor pair. I see that 2 is prime, I go ahead and I circle that. I'm going to break apart 56 again. Same rule, I see that it ends in an even number, so I know it's going to be divisible by 2. When I divide this by 2, I get 2 and 28. I circle my prime number. Now I know I have to break apart 28, and I know that 7 goes into 28 4 times. So I'm going to go ahead and write those down. I see 7 is a prime number, I circle that. And now I'm just going to break apart 4. 2 times 2 gives me 4. I circle those prime numbers. Now I'm ready to write this expression out. I see that I have 1, 2, 3, 4 2's. So I'm going to write my 2's 4 times 2 times 2 times 2 times 2. And I have a 7 right there, so I'll write times 7. When I convert this to an expression using exponents, I count the amount of 2's I have. I see that I have 4. I'm going to write 2 to the 4th power times 7. And this is my final answer for the prime factorization of 112. Question number 2 says, what number has the prime factorization 2 to the 4th power times 3 times 5 squared? Show how you found the number. To solve this, I'm going to break this apart and express this in expanded form. So I will write 2 a total of 4 times because I see that it's to the 4th power. I'm going to solve for this. I'm also going to multiply that by 3. That came from here. And then I'm going to end it with 5 times 5 because the squared tells me that there are 2 5's in this expression. 2 times 2 times 2 times 2 gives me 16. I carry down this 3. This will be times 3. And then 5 times 5 I know is 25, so this will be times 25. 16 times 3 gives me 48. I carry down this 25 and finish off my expression with 48 times 25, which gives me 1,200 for my final answer. Moving on to number 3, I'm being asked to write 4 to the 4th power in expanded form and then solve in step B. So I'm going to go ahead and I'm going to write 4 times. 4 times 4 times 4 times 4. Careful to not add. Remember that the exponent is telling us that there are 4 groups of 4 that we have to multiply. Okay? When I solve this, I get 16, 4 times 4. 16 times 4 gives me 64. And lastly, 64 times 4 gives me 256. So my answer here is 256. Number 4 asks me to write 2 different number strings that will get me 24. And you have to keep in mind that we cannot use 1 as a factor. So for my first factor string, I'm just going to do the prime factorization and see what the longest factor string would be. So for 24, I'm going to do the factor pair 6 times 4. I'm going to break apart the 6 into 3 times 2. Careful to not confuse this with addition. I know that 3 times 2 does give me 6 and both are prime, and 4 breaks apart into 2 times 2. So my factor string here for the first one will be 2 times 2 times 2 times 3. Now for my next factor one, I'm going to use this factor string and combine 2 of them. And I'm just going to say 4 times 2 times 3 will be my next factor string. You can also use any factor pair, like 2 times 12. You can use the factor pair, you can do 3 times 8, or any other factor pair as long as it does not include 1. But like I said, my first answer here is the full prime factorization expression there, and this one that simply has a few of those numbers combined. Number 5 asks me to decide whether the statement is true or false. 22 is a composite number. Thinking about composite, I know composite means it has more than 2 factors. I know prime numbers only have 2 factors, and prime numbers are, the factors are 1 and itself. So knowing this information, I have to see if 22 has more than 2 factors. So I know that I can do 1 times 22. I know that this is divisible by 2, and I can do 2 times 11. And just with this information alone, I know that this will not be a prime number. So I will say, yes, this is true. And this is true because 22 has more than 2 factors. Okay. Whoops. If you would like to include that the factors are 1, 2, 11, and 22, that would be great. It makes your answer a little bit stronger. Question number 6 says to give an example of a square number and explain how you know it's a square number. Thinking back to square numbers, I remember that a square number is a number that can be expressed as a number times itself. So an example of this is like 2 times 2, or 3 times 3, 4 times 4. So all of the answers, or the products of these pairs, 4, 9, 16, are all going to be square numbers. I'm going to answer this by saying that 16 is a square number because it can be expressed as a number times itself. And this here is 4 times 4 equals 16. I'm going to move this answer over here because there's another way to answer this. I can also say that 16 is a square number because it can be arranged into a perfect square using tiles. And the way this would look would be a model of 4 times 4, and this would give me 16. Another possible answer is to say that 16 is squared because it has an odd number of factor pairs. Now, any one of these 3 responses would be a good response as to why a number like 16 is squared. Moving on to number 7, we're being asked to list all the factors of 70. I'm going to go ahead and write my factor pairs in a list. I know 1 times the number itself will always be a factor pair for every number. I can see that 2 goes into 70 35 times, so 2 times 35 is a factor pair. Going down the list, I know 3 does not work, I know 4 does not work, but when I get to 5, I know that 5 times 14 is a factor pair of 70. I also know that 7 times 10 is a factor pair. And from here, my list would repeat. All other numbers greater than 10 are not factor pairs until we get to 14, and we would see 14 times 5, and we would see the repeat of 35 times 2. So I won't write those down. I'll stop here, and I'll just make sure that I include all of these factor pairs, going from 1 to 7 and from 10 to 70. So I'm going to go ahead and list them in order and say the factors of 70 are 1, 2, 5, 7, 14, 10, 35, and 70. Number 8 asks us to find the greatest common factor, the GCF of 40 and 52. Now, we've done this doing 2 different methods. We can either list all the factors of 40, list all the factors of 52, and circle the common ones. To do this, you could make a list similar to what we did up here with the number 70, but you would use the numbers 40 and the number 52. When you make that list, you would find that the numbers in this list are, and I'm going to make sure that I put factors of 40 and factors of 52. The factor pairs I find for 40 are 1, 2, 4, 5, 8, 10, 20, and 40. I also see that my factor pairs for 52 are 1, 2, 4, 13, 26, and 52. Now these numbers here, I would compare from each list and circle any common ones starting from the smallest number, like 1, going to the 2, I see that 4 is a common one, and I do not see any greater common factor between them. So using this method, I would see that the greatest one was 4, and I would write GCF equals 4. Now keep in mind, what you don't want to do is accidentally list the multiples. If you are listing the multiples, you would be getting numbers greater than 40 and greater than 52. To make sure that you're finding factors, you have to remember that your factor pairs are all going to be smaller than the number itself. Okay? The other method we can use is the more recent one from Investigation 2, which is using the prime factorization to find GCF. Using prime factorization, I'm going to make a tree, a factor tree for each number. I'm going to break 40 apart, which we've already done once, into 4 times 10. I'll break 4 apart into 2 times 2. I know that both of these are prime, and I'll split 10 apart into 5 and 2. The number 52, I'm going to move over just to have a little more space here. Okay, and I'm going to draw a line to separate our previous problem. 52, I know I can divide into 2 and 56. I circle 2 because that is prime. I'm going to break, oh no, not 56, I meant 26. 26, I'm going to break apart into half, so I'm going to say 13 times 2. I know 2 is prime, and although 13 is a larger number, it's actually also prime. So my factor strings for these two numbers are, for the number 40, 2 times 2 times 2 times 5. The factor string, or the expression for the number 52, is 2 times 2 times 13. I see that there are 2 pairs of 2 in common, so I'm going to circle them this way. Remember, we multiply these only twice because they're in common twice. So my GCF will be 2 times 2. So my GCF here is also 4. Now number 9 is asking what the least common multiple, or the LCM, is of 9 and 12. To find this, I would use any one of the two methods. You can either list the multiples by doing 9 times 1, which would give me 9. So for the number 9, I'll do 9 times 1. I'll do 9 times 2, which gives me 18. I know 9 times 3 gives me 27. 9 times 4 gives me 36. And we can pause there and see if there's any in common so far. I'm going to move on to the number 12 and list as many as I can to see if any of these previous numbers are in common. So I know 1 times 12 gives me 12. 2 times 12 gives me 24. And 3 times 12 gives me 36. Now, I do see that these are in common, so I know that this is going to be the smallest multiple, or the least common multiple between the two numbers. I can go ahead and write LCM equals 36. In our next method, we're going to go ahead and use prime factorization. And I know for prime factorization, I'm going to find the factor trees for each number, similar to how we did in problem number 8. I'm going to break apart 9 into 3 times 3. Both of these are prime, so I can circle them. 12 breaks apart into 3 times 4. 3 is prime. I can break apart 4 into 2 times 2, and those are prime as well. My factor string for the number 9 will be 3 times 3. My factor pair for the number, or my factor string for the number 12 will be 2 times 2 times 3. Keep in mind, to find the LCM, you'll have to find the GCF first for these numbers. And in finding the GCF, I have to circle any common numbers between the two expressions. I see that 3 is in common between both. So my GCF here is just 3. Remember, this is only 3 because there's no other number or no other matching factors that we can multiply with. Now that I've found my GCF, I can move on into my LCM, which I know is GCF times any leftovers. I'm just going to write that as LO. I know that my leftovers here in my list are the numbers 3, 2, and 2. So for my GCF, I'm going to go ahead and write that this was 3 times the leftovers once again are 3 times 2 times 2. This means I'm multiplying 3 times the product of these here. 3 times 2 is 6, and 6 times 2 is 12. So this will be 3 times 12, which tells me that my LCM now that I solve for 3 times 12, is 36. And notice how we got the same answer using the traditional method by listing the multiples, and we also got 36 by using prime factorization. For the number 10, we're being asked that if you're given the problem 7 times 7 times 3 times 3 times 3, without actually solving the problem, how can you tell whether the answer will be odd or even? What I want everyone to think here is what each outcome was when we tried to see what an odd times an odd number was, what an odd times an even number was, and what an even times an even number was. Thinking about odd times an odd, we can try any number here, like 3 times 3. This gives me 9. So I know anytime we see odd times odd, this will give us an odd number. Odd times even, I'll try the numbers 3 times 4. This gives me 12, so I know odd times even will give me even. And then when trying even times even, like 4 times 4, I get 16, so I know the answer is going to be even. Now seeing these things here, odd times odd is odd, even times odd times even is even, and even times even is even, I can now try to see what this will break apart into. So I'm going to do 7 times 7 and see what this gives me, times the product of 3 times 3 times 3 to see what this gives me. I know that 7 times 7 is 49. I also know that 3 times 3 is 9, and 9 times 3 is 27. So here I see that this is an odd number, and this is an odd number. What this means is we are multiplying odd times odd, which tells us that when you multiply odd times odd, we are most likely to get an odd number because of what we found before. Now that I've done this work, I can go ahead and try to explain it. I'm going to explain this by saying that the answer will be odd because seven times 7 is odd, and 3 times 3 times 3 is also odd. When you multiply these two, odd times odd, the product will also be odd. Up next, we have a question on order of operations. We're being asked to solve 50 minus 2 cubed divided by 2 plus 10 times 3. Now, looking at this problem, there are two approaches. Some of you have used the GEMS approach. Some of you have used the PEMDAS approach. Whichever the two you have used, just pay attention to each method that I try. I'm going to go ahead and start with the GEMS first. So if you are someone who's more familiar with PEMDAS, you can go ahead and skip forward a couple of seconds and see the PEMDAS explanation. If you use GEMS, we're going to get started with it. Now, just as a reminder, G stands for any groupings that we see. So this is anything in parentheses. E is for exponents. M is for multiplication and division. And S is for subtraction and addition. Okay? So starting off with this here, we can see that there are parentheses there, but there's nothing to solve inside of it, so the number is just 3 by itself. So we know that there is nothing to do with the number GEMS, or with the letter G for groupings. We move on to the E. We do see that there are exponents. I see that 2 is cubed, so I'm going to go ahead and solve for 2 cubed. And I know that 2 cubed is simply 2 times 2 times 2. So I'm going to rewrite this as 2 times 4 is 4, and 4 times 2 is 8. So I'm going to write the number 8 down below here. And then I rewrite the rest of this expression in the same way. Plus 10 times 3. I see that there are no more exponents to work with, so I am all done with the exponents. I move on to the M. I do see that there is multiplication and division. The first problem for the division is right here. Actually, it's 8 divided by 2. I also see 10 times 3. Now, because we are working from left to right, we're going to start off with 8 divided by 2, which I know is 4. So I'll write the 4 down below, and I know that the rest of this stays the same. So I rewrite 50 minus that 4 that we got from 8 divided by 2 plus 10 times 3. I check back to see if there's any more multiplication and division. I see that there still is multiplication here, so before I can move on to subtraction and addition, I'm going to go ahead and multiply 10 times 3. This does give me 30. The rest of the expression stays the same. And now I'm left with just subtraction and addition. So I am all done with multiplication. I'm on subtraction and addition. I'm working from left to right. So I'll start with 50 minus 4. 50 minus 4 is 46. And I bring down the rest of this, which is just that 30. And now I can solve 46 plus 30 is 76. So like I said, this is one approach that you might use in class. If you did use this and you have a good understanding of it, you can go ahead and skip the next explanation here, the next method that we're going to use, which is the PEMDAS. Now, using PEMDAS, it's very similar. We know that this is for parentheses. The E is for exponents. M is for multiplication. D is for division. A is for addition. And S is for subtraction. We also know that we do everything in parentheses by itself. We do everything in exponents as itself. But when we get to multiplication and division, we think of these as a pair combined. So it can be either multiplication or division. And when we get to the addition and subtraction, those are also a pair. So any addition or subtraction, we work from left to right. Okay? So I'm going to write my my expression here. 50 minus 2 cubed divided by 2 plus 10 times 3. I'm going to go ahead and I'm going to look for anything in parentheses. Like I said, this has already been solved for, so I really don't have to worry about it. I know I'm done with parentheses. I can move on to exponents. I see that I have exponents right there. I'm going to solve for this. I know that 2 cubed is 2 times 2 times 2, which is simply, like we previously said, 8. So we'll rewrite the rest of this. 50 minus 8 divided by 2 plus 10 times 3. I see that there are no more exponents, so I'm all done with the exponents now. I'll move along into the multiplication and division. Any of these two will be done from left to right. I see that I have division. I also see that I have multiplication. Because division comes first from left to right, I'm going to solve for this first. 8 divided by 2 is 4. I'll rewrite the rest of this equation. And I'll continue to see if there's any more multiplication or division. Now, keep in mind, anytime you have a number outside of a parentheses, in the way we see here, 10 parentheses 3, we're going to multiply. This here does give me 30. I rewrite the rest of this expression, and I am all done with my multiplication and division. Now I go ahead and look for any addition or subtraction, also going from left to right. I see that there are 2. I see 50 minus 4. I see 4 plus 30, but I'm going to go ahead and start with the 50 minus 4 because we're going left to right. 50 minus 4 is 46. I rewrite the rest of this, and now I can solve for 46 plus 30, which gives me 76. Either one of these two methods will get you to the same answer, and either one of these two will give you full credit for that question. Number 12 says, which of the following expressions are equivalent to 9 times 50? So this is what we're looking for. We're going to circle the expressions that are equivalent to it and use order of operations to prove our reasoning. So the first step in this is going to be to actually figure out what 9 times 50 is. So I know that 9 times 5 is 45. Because this is 50, that must mean that our answer is going to be equivalent to 450. So we're looking for which of these expressions are equivalent to 450. Now once again, both the GEMS and the PEMDAS method will get you to the right answer. So if we take a look at letter A here, we see that there are two operations being used. We see there are multiplication and addition. So in either of these two, we know that we are going to start with multiplication first before we do any addition. And because we're going left to right, we're going to start with 9 times 47. When I multiply 9 times 47, I get a product of 423. I go ahead and I write the rest of this expression down so that plus 9 comes down, that times 3 comes down. And now I see that there is still multiplication. I cannot move on to the addition until I am done with this. So I'm going to go ahead and solve for 9 times 3. When I do 9 times 3, I know that this is 27. So I'll write my 27 plus the 423. I am at the addition step because I have no more No more multiplication. I also see that there are no parentheses or exponents or groupings. So the final step here is just to add. And when I add these two numbers, I do get 450. Now we're going to continue and solve to see how many more of these also equal 450, but we see that this is the answer we were looking for. I know that this could be one of the expressions that is equivalent to 9 times 50. When I go ahead and do letter B, I see that there are two different operations. I see multiplication and subtraction. Don't forget that anytime you see a little dot, it's the same thing as multiplication, written as an X. It's just another way of writing that. So don't get those confused. We are going to work from left to right. We see that multiplication comes before subtraction on both the PEMDAS and the GEMS model. So I'm going to go ahead and start with 10 times 50. When I do 10 times 50, I get an answer of 500, and I carry down the rest of this. I see that I still have multiplication, so before I can move on to the subtraction, I'm going to multiply 2 times 25. When I multiply 2 times 25, I get a product of 50, and I rewrite the rest of this. I'm all done with my multiplication. I can move on to the subtraction and simply subtract 50 from 500, which gives me 450. This is also one that appears to be equivalent to the product of 9 times 50, so I'm just going to make a little a star next to it just to separate it from the ones that might not be. Moving on to C, I see two operations. I see that we have multiplication and addition. Once again, on GEMS and PEMDAS, I see that multiplication comes before addition, so I'll go ahead and solve for 9 times 50 first. 9 times 50 does give me an answer of 450. I write the rest of this expression down. My final step is to add. When I add these two numbers up, I get a product or an answer of 453, which I know is not equivalent to 450. Moving on to letter D, I see a new operation here. I see that there's a grouping or parentheses. I see multiplication, and I see addition. So I have the parentheses here, the addition, and the multiplication. Of these three, using GEMS or PEMDAS, I know that grouping comes first or parentheses. So I'm going to go ahead and solve for the inside of this first. I know that 47 plus 3 gives me 50. I'm going to keep my parentheses around that 50 and rewrite the rest of this. I now see that there's only one operation left, which is going to be multiplication. And just to show you, the multiplication did come after the parentheses or the groupings. So we can go ahead and just solve for this and do 9 times 50, which gives us 450 as well. So all of these expressions here, D, B, and A, give us an equivalent expression to 9 times 50.